Before we kick things off, I've got 2 quick things for you. First, do you want to push real innovation and help spark the uncomfortable but necessary conversations in the concrete industry? Support this show. When you donate, we list you as a producer of the episode because you're literally making these conversations happen. Go to concretelogicpodcast.com/donate and back the show today. Second, for a limited time, you can get free access to the Concrete Logic Academy. Take your first class on us, earn a PDH credit, and stick around for the networking and resources you won't find anywhere else in the industry. Claim your free trial now at concretelogicpodcast.com/academy. All right, let's get into today's episode.
What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandett.
And welcome to another episode of the Concrete Logic Podcast. And today I have the one and only Dan McCoy coming back.
Coolest guy in the concrete industry.
Yeah.
I am going to vehemently deny that. That is not true, everyone.
Okay.
All glorious
How
freedom.
about this? You're the coolest one in this group.
That's nice, but it's not true.
There you go.
I'm gonna stay on that.
And Dr. Jon. Dr. Jon's back on the show. This is
Who
his
cares?
100th show.
It's got to be close to that. Like he is. Oh, blue filter. He. You know, it's like the SNL. Like who's hosted the most SNLs? I swear he's like the most often host. I mean, look how he's behaving now. It would be hard to believe. Second cross.
Yeah, I don't even know what he's doing. I didn't even know this.
Belushi and Hanks.
The software could do. Don't do that. You're on some rinky-dinky internet out there in Indiana. It's going to break it. We're lucky to get you on video. Yeah.
How many times have we tried to do that and it didn't work?
Well, so today, the reason I got these two fellas on, I got an interesting text from a colleague who I was sharing information that Dr. Jon sent me on colloidal silica and sent it over. And the response I got was Silica Fume is a cheaper, better option. So today we wanted to talk about, I think first off, if we could talk about what Silica Fume is, where it comes from, how it's used in concrete, and then we can do the same for colloidal silica and do a comparison with everything in life. There's not perfect solutions. There's only trade-offs. So let's talk about those things too. Dr. Jon, why don't you tell us what Silica Fume is?
Can I define both Silica Fume and colloidal silica, bookcrete, labcrete, and then Daniel, you take realcrete, streetcrete?
Sure.
Sounds like a plan.
So Silica Fume, without using ChatGPT, is a byproduct of ferrosilicon alloy production. As I understand, it was originally brought to the concrete and construction industry from Norway and China by a gentleman named Per Thittestål. And what they used to do is they used to outgas this fumed silica, or the silica used to just go out the smokestacks and used to fall on people's cars. So Per collected this shit, started putting it into concrete, and then from there they started finding, the benefits of it, whether it was densified or undensified silica fume. And ultimately it's either undensified, densified powders, or you can have it in a silica slurry. It could be anywhere from, I think, 89 to 98% or 95% pure silica. It normally comes with a certain level of contaminants. And the reason why we like it is it's an amorphous form of silica, meaning it's in a state that is ready to react with calcium hydroxide as a byproduct of our cement hydration to create more of the backbone of concrete strength, the calcium silicate hydrate. The difference between that and nanosilica, most of the silica fume that we use is on the micron size. Some of it, the tail end of it is on the nano side, but the bell, the fat bell, and the other side of the tail, it's all big micron size particles. When you compare that to nanosilica, we are only in the nano range between 1 and 100 nanometers on the bookcrete side and 3 to 100 nanometers on the labcrete side. And because of that, one, we don't want to use it when it's in a powder. We use it in a suspension called a colloidal suspension of silica, so colloidal silica. And it has a surface area 1,000 times greater than that of silica fume or fly ash. Now, the last piece of it, the last two pieces of it is, one, much higher purity because we are manufacturing something. This is not a byproduct. We've been using it for decades upon decades, since the 1800s. And if you eat ketchup, use printer ink, drink wine or beer, you've had colloidal silica because it's used as a clarifying or a suspension agent. Now, one other thing, and I'll shut up in a second, Daniel, because it's on the nano size, we have a higher degree of pozzolanic reaction, a faster degree of pozzolanic reaction, and we get a higher degree of accelerated cement dissolution, meaning we get more bang out of one cementitious buck, ultimately creating an environment for a concrete that is stronger and lasts longer because of its resiliency to physical and chemical attack. Did I miss anything? Do you have any questions?
No.
I think that was
Dan?
excellent. No, I think that was excellent. So I think going back to the comment, Seth, about, and that's what you get for anything, right? What's the value? Where's the benefit? And I will tell you that from my experience, the one thing that we relied on silica fume very heavily for was bridge deck overlays. I don't know. I cannot answer you. This is why I went through my whole iteration in 2019 through 2020 about what are we asking? What are we asking this concrete to do? There's some significant benefits with silica fume as far as strength production, and I get that. But the way it's treated mostly is in an addition. It's not so much a supplementary cementitious material to supplement that powder. It's normally used as an addition. In a standard bridge mix, there's a really good study, and I wish I just tried to look it up and I just crashed my file explorer trying to find it. But there's a really good study that involved in the 1970s what silica fume and bridge deck overlays does. And then can we incorporate the silica fume into normal concrete as well? So normal bridge deck concrete. What you found in the difference was back then, it's kind of changed. As Jon mentioned, you can have densified, undensified, slurry form. Normally in the 70s and 80s, you ended up with a slurry form where the producer, the concrete producer, would use it in slurry form to inject it into the ready mix as it was ready to leave the plant. Nowadays, it comes densified and it's ready to go in a water-soluble bag. The problem is when we look at some of the things we do, one of the things that's needed to break up that bag is, and usually an agent that is going to beat the hell out of the bag. Normally, that would be a larger coarse aggregate and a combination of a medium coarse or a medium coarse aggregate. So what we found out with the overlays was we did everything you weren't supposed to do with silica fume. So we really didn't give it a good chance. We used it in a very high dosage. It was yeah, that's it.
Yeah, that's why I'm shutting off my cameras. I'm trying to save bandwidth to get this fucking stuff.
Well, boy,
So
see, but a lot of people, I listen to Seth's podcast on my earbuds. So when you point to something, on the screen, now I can't point to it. But let me read the title for everybody. So this was Silica Fume Microsilica Concrete in Bridges in the United States. And it was from the 1970s, 1980s.
Well, look, 5 to 15.5%.
5 to 15.5% by volume. And they were, almost all of those dosages were, like I've said, normally when you're dealing with a slag or you're dealing with a fly ash, those are replacements. Usually with silica fume, it's an addition. So in the overlays that we ran into trouble with, they were high concentrations of 7%. silica fume addition. So you took a 658 mix plus 50. Now you're sitting at 708 pounds of cementitious with a silica fume that likes to be volatile. It's water hungry. And then the next thing you try to do in the warning on silica fume is, don't try to use it with a low water cement ratio either. Well, we end up using.
Oh, look at this, Daniel. Did you see that water cement ratio?
Yeah. So these water cement ratios are 0.35, 0.34, 0.33. Those are all very common. But I wanted to, the difference between what John's showing in that paper and what we're doing now is they generally use, and they get into it a little bit, about the use of a densified versus undensified versus a slurry form. And many of those were slurry forms. So they did go in as almost as a saturated condition. And one of the things that I get concerned about is we're already using a low water cement ratio. Yes, it's attained with that, but now it's attained with that low water cement ratio. We're using that 708 pounds of cementitious full as incorporating it. And now we're looking at the aggregate that we use for an overlay, which is a fairly small coarse aggregate. It's like a 3/8. So we're doing everything wrong to the silica fume. We're not really giving it a good chance in overlays. And one of the reasons to put that in there was to slow down corrosion, right? We wanted our rapid am I going too fast for you, Seth?
No, keep going.
No, keep going. So one of the things we wanted to do was look at our chloride penetration before that, because we're going to deal with a lot of that in the roadway. That's everything that was done in the mix design to try and protect the surface. Now, what happened in the field a lot of the times was that it was I used to call it, I'm a nuclear fan, so I used to call it tickling the dragon's tail, right? Every time you deal with a mix that's that volatile, it can turn on you in a hurry. So if the water cement ratio ends up being a little less than what you thought, or a little more than what you thought, and now you have runaway evaporation, and evaporation rates increase, the silica fume increases the internal temperature of the concrete with its reaction. It just lights it on fire, right? You end up with internal temperatures of like 150, 160 degrees. In an overlay that's only supposed to be, picture this, that's only supposed to be 30 feet wide, maybe 100 feet long, but it's only 1 3/4 inches thick. Where's all that shrinkage happening? Eventually that evaporation has to leave, the water has to leave. And that's what you end up with. It's very prone to shrinkage cracking and plastic shrinkage cracking. Now in before, one of the things we always did to fix that was go back later with an epoxy penetrating sealer. The breaks that we were getting on those, they were outstanding. I mean, we're talking 9,000 PSI. But you have to ask, again, what do I want to get out of this concrete? And for the overlay, all I needed, there were studies in Missouri saying that they were opening to traffic on pavement that was at 2,500 PSI. Well, if I can do that, God, all I need is 3,500 to 4,000 PSI. And I don't want to, and John just put something else up that was really great by Jan Olich. So when you're looking at the strength differential between your subsurface or your structural slab and your wearing surface, you don't want too much of a difference in there, right? You don't want too much of a delta between those two. And they're acting different. They're made of different materials. There are some nasty things that happen in that interface. So that's why instead of going with the silica fume, now that the author of Who Questioned You of What's the Benefit, it's again the argument of I'm not chasing compressive strength. I don't care about that. What I'm looking for is what do I want to use the concrete for, right? Performance-based specifications. I want it to be 3,500 to 4,000 PSI. I want it to have low shrinkage rates. I want it to not be when I say low shrinkage, I want it to be not susceptible to plastic shrinkage, because the way I'm using this, I'm submitting it's a lot of surface area for the amount of volume. So this is what you're asking of it. So that's where it became a lot better to lower the cement content, take out the silica fume that was somewhat volatile. That's just for us pouring it. It doesn't say anything about the actual production process, which I'll get to just after I explain why this colloidal silica was used instead. So then we use a colloidal silica that was replaced at, I think 4 ounces of one that was blended for internal cure and 8 ounces of one that is known commonly as liquid fly ash. Those are colloidal silicas. So with 12 ounces per hundredweight dosage of a colloidal silica, I'm able to get rid of a lot of those problems and get what I want, which is a wearing surface, right? When we look at a micro or a nano scale, the cracks that you would see in the micro cracking that maybe you couldn't see from a micro silica fume, that would inevitably happen either between the tines or when you start to groove. Those cracks to a chloride and a water particle are absolutely like the Grand Canyon. You're just letting them all in. Now, the whole thing we tried to do was reduce permeability with our silica fume. Well, we're defeating the purpose. I mean, if we build the world's strongest wall, but then we put slits through it that anybody can sneak through, I don't know what good the material of the wall did, because it's not there where anything's sneaking through. So that's we said if we can reduce that cracking and the cracking potential, maybe even throw some fibers in there to give some more nucleation sites, so that can hold a little bit better. I want to go to the production side, to where you throw in those silica fume bags, and the guys don't, when I say the guys, I mean, the ready mix producers really don't like handling them. And I totally understand. So what you end up with is, picture a truck, dry, wet batch, it doesn't matter, but it goes in. The silica fume is not usually in a silo, right? It's usually an on-demand type of thing. So it's sold in pallets. So now you've got to find a place to store and keep these pallets dry. They're in bags. So depending on the dosage, now either someone in QC at the plant or the driver himself has to actually physically get out and load these bags up into the hopper of the ready mix truck. Now, I've seen things before where, well, what do we do with these bag corners and these bags that don't really dissolve that well, because we're using lower water cement ratios for this type of thing. That was the old game, and you didn't want to use too much water, because then you could induce runaway evaporation and shrinkage.
In all fairness, they've taken care of the bag dissolving issue, but you cannot get past, and I'll shut up, the safety issue of some guy walking on the catwalk or climbing up in the middle of the morning, throwing bags in a safety vest underneath a central plant mixer. That itself, I don't care how the bags dissolve, you're never going to get past that. Go ahead. Sorry, Daniel.
It's an additional labor load. So is a higher cost, not for the material, but just working with the material. If you give guys at a plant any choice on whether, hey, do you want to rig up, basically an admixture in a tank that's plumbed in for our admixture system, or do you want to physically and manually load bags? And then if you do use a lower
density.
If you use a lower water cement ratio and you want to get rid of the bag issue because you're tired of finding bags, then you split the bag open and then you're pouring it in. Now you've got other concerns with micro dust particles that cause a little bit of a health hazard to the people.
And then if you want to go to a slurry, normally those slurries have to be delivered the day of, the morning of, the week of. And sometimes when deliveries go to shit, because they don't stay in suspension very well. So when deliveries get delayed, the job site doesn't continue. That's what we had in the greater Toronto area. They were using silica slurry. Material got delayed because of traffic. And they're like, hey, we have this colloidal silica, this E5. And holy shit, they used more than we recommended, and they fucking fell in love with it. Stickier than any freaking shotcrete mix they ever used.
Sorry, I didn't go to that. So yeah, when you're placing, silica fume has a tendency to be a lot sticky. Like if you're listening to this right now and you're a residential or commercial guy, and you've never done DOT concrete, the first time I ever I've only done DOT, and then the first time I ever put a mag on some commercial concrete, I was like, oh, this is really nice. Because everything I was used to for years was just a sticky mess. And that's just what you were used to. And because you had a lot of that going on where you poured in a very low slump with something like a silica fume in there. I wanted to get back to, this is going to tie in Bob Higgins' work with sublimation along with.
But can we do cost real quick? Because that's what I think Homeboy said before we talk.
Homeboy said about cost, but I want to tell the difference in the benefits between. I'm not so much getting on silica fume, but I'm getting on the benefits of what colloidal silica does. And I want John, I'm throwing him a curveball here, but we talked about sublimation, Bob Higgins did, about even just the light source. It's one of the things we're concerned with that lighter evaporation of the concrete, even at the surface. So what I want to throw to Jon is, Jon, why don't you tell everybody a little bit about what colloidal silica does with the water, i.e., the glassy nature of water.
So there's a wonderful effing paper that was written by MIT. It was something Palank. I can't remember his first name, but it was on the glassy nature of water in cement. And there's 3 types of water that we know about in cement. There's bulk water that can freeze and thaw and can cause erosion, corrosion, alkali silica reactivity. Then there's chemically bound water. That's water that's not necessarily water, but definitely isn't a solid yet. And what it's happening is that it's being incorporated into the chemical reactions, whether that's alkali silica reactivity, or in our case that we like, the superhero of concrete, calcium silicate hydrate. Then there's chemically incorporated water, which it's not really water anymore. It's water that's really been trapped in the fractal network of our calcium silicate hydrate, because calcium silicate hydrate is not a crystal. In the best of papers by I.G. Richardson, Andrew Allen, they talk about calcium silicate hydrate as an amorphous-like crystal, meaning it's more disorganized until you go to a really, really, really small level, where at the nano level, it starts becoming a little bit more organized. When we look at the micron scale, within that fractal network, there's chemically incorporated water that's restrained within about 3.4 nanometers. Now, according to this guy Palank from this paper back in 2007, 2008 about the glassy nature of water, when we confine water into these small areas of concrete and that water can't move, now it goes from having the ability to freeze, thaw, corrosion, erosion, and other shit to providing strength to the concrete because it has this more glassy or ceramic nature. And that paper, they went as far as identifying the strength of that water that was ultra confined. I'll try to find that paper here in a second. Go ahead, Daniel.
No, so that's what I was going to get to. Now, when it comes to costs,
Wait, Seth had a question.
Yeah,
Sorry,
I
Seth.
think I found it. Is it the Bordalo or whatever paper?
Don't say Bordello.
Share it real quick.
I don't have the paper. I'm just searching.
Oh, he's looking for it. So while you two were finding that, I'll just go on and define. I think one of the things that was questioned was the cost versus the benefit. And yep. I guess I was excited about the question that Seth you received, because I know we're a fickle industry and we only care about costs for the most part. And ironically, in this case, usually in my bridge concrete, suppliers, meaning ready-mix producers. Sorry, I get that wrong all the time. I call them suppliers. Jon calls them producers. So ready-mix producers, they tend to have higher prices with silica fume because of the nature of purchasing the product, storing the product, and administering the product, because it's not put in every mix. So usually what I see, like if I would take a normal, let's say what I would call my touchy mix, the one that I just went over for our old overlay mix, that on average was, close to, this was several years ago because we pretty much replaced it, but you're at basically $250 a yard for something like that. And then we come back and we look at the one that was kind of designed to work with that, with the colloidal silica replacement. And now you're looking at something that was, back then, just to compare apples to apples, was like $165 a yard. So not only was it better performing for what we wanted the concrete to do, it was also less expensive. Right?
And we could do the math on the cost of it real quick. I mean, let's say if we assume the bought price was $500 a yard and the sold price, the retail price is $1,000 a yard. Here it is. Oh, wait. No, that's not it. I mean, that's a pretty easy calculation if you guys want to go through that math real quick.
No, I think I just did it with the real world, but you could.
Yeah, I did it the other day. It was like $23 or something like that per yard. Go ahead.
Let's a couple things push back on you, Dan, a little bit. So your experience is with Silica Fume, is it solely on the bridge deck overlays with being, would you say 1 3/4 inch or something like that?
So there was also so it's bridge decks and bridge deck overlays. The bridge deck overlay was, like I said, I don't think we give Silica Fume a fair shake. So if there's any
Right.
Silica Fume lovers out there, I don't think we
Well,
gave it a
Rob.
fair shake because we used way too much of it in that mix design. And now the bridge design mixed concrete, that was also thrown in. You had a choice back in the day. You could use a 658 with either a 3% Silica Fume addition, or you could use a 658 with a 30% slag replacement. And all of that was meant to chase permeability. So that's and even on the bridge deck concrete where it was 3%, addition, it was still a pretty hot mix. And that's one of the things that I want to be careful with. I mean, it was literally a hot mix. That's one of the things that I want to urge, with caution with people that want to use a Silica Fume now with, say, a blended cement, like a Type 1L blended cement. We've got finer particles. So we know, and we've looked through maturity, we see higher temperatures, early onset temperatures, with correlating lower strengths as compared to a maturity curve from a Type 1. So we end up with higher Fahrenheit hours or Celsius degrees. We end up with higher with lower strengths in those early phases. So that higher strength is that higher temperature is what I get a little concerned about, because those are the things that early onset lead to, some plastic shrinkage. And then it also leads to thermal shock. And one of the things I don't want to see is I don't want to see a large variation regardless of the volume of the pour. Don't want to see a large variation between the ambient temperature, the temperature of what I'm placing the concrete on, and that heat of the concrete several hours after placement. And usually with a Silica Fume mix, you see higher induced temperatures as we go 4, 5, 6 hours afterwards, up to 145, 150 degrees. When you know that even in a large mass pour, which I think ACI just defines as 18 inches, I can't remember. But if it's the thermal differential that you're looking for of about, I just judge myself, if I want about 30 degrees. Well, if I'm only playing with a 30 degrees difference and it's a 75 degree day out and I've got my temperature up at 125 degrees 6 hours after pour, I'm a little worried about it, right? I'm trying to make a good pour out of it. So the better I can keep that concrete temperature post pour with the ambient temperature, or at least maybe not let the ambient temperature have any say in it. So that's where you come either with your cooling or you come with temperature control about insulating. So you have more of that. I remember talking to NDOT thinking, well, we're trying to control that. So maybe do we need to just limit our pours to, for overlays to be less than 0.05 for our evaporation rate? And then do we need our ambient temperature to be less than this? I mean, if we took everything that we needed to make it work from an environmental situation, we would only be pouring between, let's say, March 31st to maybe May 1st at night between 2 and 4 in the morning, depending on what the wind speed was. That's literally
8 p.m. at night till 4 o'clock in the morning would be, you'd have a nice window.
Well, but you say 8 p.m., but you're forgetting. Well, the one thing you have to do is let the aggregate cool down, John. Now we've had this aggregate that's been heated all day in piles, and now we're going to start pouring at 8 o'clock. Just because the sun went down doesn't mean that the aggregate didn't retain that temperature in the mix.
But they could do that with sprinklers. They could shade the aggregate. I mean, that they can handle ahead of time, Bubba. Don't worry. We got it. You just let us know when we can deal with traffic, because that's the hardest part, is getting the trucks on
and
the road.
Traffic is a huge concern when you're trying to time these mixes out. Like I said, I think when I said tickling the dragon's tail, I was serious. It's just a volatile mix. The more Silica Fume that you throw in.
Tickling the dragon's tail in the nuclear
Okay,
world?
well, so at Los Alamos, they would do these things to judge critical reactivity. So they would. Okay, well, they would place, a little plutonium core, and then they would reflect all the neutrons coming off of it, and they would see how close they could get to measure that reaction. It was tickling the dragon's tail because, if you drop that, you went critical. And then you created this blue ionization that would spread radiation throughout the air. It's actually pretty fascinating if you look it up, but it's, to me, an unnecessary risk given the objective.
Wasn't there a movie about that with John Cusack?
You're right, it was. John Cusack and...
I'm looking it up.
Paul Newman? Paul Newman was the general. I can't remember, but anyway, that's what it was. And I think I think that's what we do with some of these pores when we don't look. We, meaning engineers and asset engineers, and say, what do we want the goals to be for this? What performance do we want out of it? And you'll generally find that with a more flexible mist at a lower compressive strength, with less vulnerability to cracking and shrinkage, you're going to get a better, longer-term performance out of your wearing surface, because that's what we're dealing with. Now, the same thing could be said for bridge concrete as well. I mean, all you're really reaching is, an everyday 4,000 PSI. But we try to make it complicated because it's bridge concrete, so it really doesn't have to be.
Well, or we can
really
overcomplicate it.
So using colloidal silica gets rid of some of those complications.
And when it comes to silica fume, if you really stick to the Silica Fume Association manual, folks don't use silica fume right. It's not just the bags. It's when you're supposed to have the cement touch the other raw materials, and it's rarely at the ass end of the mix. And that's what normally everybody does. It's supposed to be in the head. And even when you put it in the head, Dan was already talking about, hey, those bags still dissolve, but they don't dissolve very quickly. They're designed not to dissolve quickly because they're transported in a very extreme environment. So inevitably, you don't get the silica fume doing what it's supposed to unless you're willing to plummet into. And that requires either a pig or a silo. And who the F is ready to do that? And
I mean, ironically.
Wait, there was one guy for a long time selling silica fume to the U.S., and he's the guy who wrote the Silica Fume Association manual. His name was Tony Kajundik. And in lieu of selling it to the concrete industry, he started selling it back to the steel industry because they didn't give him any problems. They know how to use it, and they were consistent. Concrete isn't. Go ahead, Daniel. Sorry.
Yeah. So ironically, if you could put it in a slurry form, you could also use colloidal silica then with your microsilica slurry form to leave it in suspension longer. So I guess there is a benefit if you use slurry.
Use them both.
But I really don't think that's necessary. I think that there's definitely, I think one of the other things that was said from your comment, Seth, that you got was the environmental benefit of using the silica fume because it was a byproduct of the smelting process, right?
Yeah.
I don't give anything a free pass. If you're going to be a true environmentalist, you have to look at everything. So just because it's a waste product doesn't mean it gets a free pass. In my mind, what did it take to get that 1 ton of silica fume? And usually it's a 1-to-1 ratio with cement. It's about 0.9 to a pound of CO2 per pound of the silica fume.
Where'd you pull that from?
Yeah, I think it's much lower than that, Bubba. I would love to be wrong.
Well, 0.5 to 2.5 tons of CO2 per ton of microsilica.
5 to 2.5. Are you looking that up at
It's a wide range. When I did it before, it was You guys push back on me, but I mean, when you think about the smelting process, you have to include that. I know that they don't. They consider, well, that's downstream and it's a waste. But if we're really fighting CO2, we should do everything we can to remove all CO2 production.
Yeah, I agree with that. They put all kinds of garbage in concrete to save the planet.
What's wrong with that? Concrete is a great garbage can.
I guess.
It is, but I think it's, are you a true environmentalist?
As long as you admit it.
Yeah. Right.
When they were putting CO2 into concrete or tires. Oh, that tires thing killed me. Okay, what am I looking for? EPD?
Yeah.
Yeah.
Yeah, EPD of silica fume. This is fun. This is on the fly learning. Seth, you can cut this out later so it just cuts to John and he just sounds brilliant.
Yeah. If you do chat GPT, it says silica fume is 0.02 to 0.05 pounds.
Yeah, we don't want pounds.
CO2 per pounds. And then
okay, CO2 per pound. So let's do it this way. We convert 658 divided by 1.68588. You got 400 kgs. Right?
Mm-hmm.
So what did you say your number was? 0.02?
And I just call it 0.03.
So that's 19.74. Then you divide by 1.6588. That still sounds like bullshit.
Yeah. Well, it's this thing searches the same.
But keep in mind that most of the mixes, and I mean a majority of the mixes, use silica fume as an addition, not a replacement. So no matter what we're doing, we're increasing the CO2 in that yard of concrete.
We wrote an article on this for ACPA. Daniel, do you remember that? The American Concrete Pumping Association.
You know, there's a lot. There's the Concrete Pipe Association,
Pavement
Association. There's a lot of ACPAs.
Oh, here you go. So I asked ChatGPT where it got its information on the CO2 per pound for silica fume, and it pulled the data from the company that sells silica fume.
Yeah.
Well, that's who is supposed to have it, but we need it in kg of CO2 per pound. So
Yeah.
what did you say? It was 0.02. It should be.
You want the GWP is what you're asking for.
Right. The kg CO2 equivalent per pound.
Well, per, what is it? Elchem? The company sells it?
Elchem, the Elchem or Ferroglobe. That's who Uncle Rob used to work with, was Elchem. So it should be.
The high end, they're saying 0.10 kilograms of CO2 per, whatever.
No, the whatever is important. Is it pound or kg?
Kg.
Okay, so it was 0.1 whatever?
0.
How many pounds or kgs are in a pound? 2.2?
No, it's the inverse of that. 2.2 pounds in a kg.
Yeah,
That's
if you
what it
want
just
the
said.
equivalent in pounds, it says 0.045 pounds of CO2 per
There's
pound.
no fucking way. Dan's right. They're skipping some very important step.
Well, I'll
Just
send
because
you the
it's
link
a byproduct doesn't mean you get a free pass. Like, what the fuck, dude? Even Pond Ash has a 0.21 and cement has a 0.42.
I completely disagree with that because you have to burn coal to get ash. So you're looking at 17
and then you have to reclaim it and clean it.
Ash.
It should be equal to.
Still, if you're going to be a true environmentalist, you better go with it. If not, shut your mouth.
Yeah, fly ash has the lowest. Per this.
Fuck bullshit, man. That's such horseshit.
Hey, come on.
And you know, nobody is looking past.
Let's be nice. We've got kids listening to this show.
Great kids. Uncle Jon is here, and let me teach you the use of a good word called horseshit. When somebody's lying and you just don't know what to say to call them out on their bullshit, you can yell emphatically, "Horse shit!" That's from your Uncle Jon. Make sure you tell your parents.
So Seth, this is exactly how we remain on the naughty list, and this is why Bob Higgins has such great shows. I mean, he just gets so. I'm
all right with that,
and enthralls me. And you get us two morons on, and it might as well be a comedy podcast that isn't even funny.
You know, you've got to have a little levity with the bullshit that we deal with, right? Like, if you can't laugh at it, you're going to freaking cry. Like, okay, can we just talk about this concrete right here?
Sure.
Like, look at this.
Wait.
Hold on.
I wanted to dig a little further. I want to answer Dan's question about how many pounds of CO2 are in coal. Because you got to start there, right? How many pounds do you guys think of CO2 per pound of coal?
Coal what? Coal
it's
consumption?
Tremendous.
3.
Well, but what is that? Coal consumption? Coal what?
No. It's so it's like a British thermal unit. As it sits there, what's the potential energy? And that's what it's saying.
Okay.
Burn it off.
So
if you burn it off, here's what you've got.
So if that's 3 kg of CO2 equivalent,
right? But
kg,
how much coal do you have to burn?
That's pounds. That's pounds.
Right, and how much coal do you have to burn to get 1 pound of fly ash? That's the key. So I have to burn how many pounds of coal?
That's a great fucking question.
At 3 pounds, how many pounds?
What's the efficiency
to get 1 pound
of
the fly ash that's left over? That's where I think I came up with my number roughly of 17 or something.
Man, we're going down a deep rabbit hole here.
I know.
But
everybody else
doing this, man.
What is it?
When you read ACI 323 that really governs this mishpacha, this mishagas, they'll even tell you, well, we don't consider that because we don't have all the data.
Oh my gosh.
How many pounds of
for
coal?
every 1 pound of fly ash, you need roughly 8 to roughly 8 to 20 pounds of coal.
So there
Yeah,
you go. 8 times
buddy.
3, 20. That's 24 pounds of CO2 for 1 pound of fly ash.
And convert
That's
that
pretty
to
basic.
kg, that's 12. That brings it to 12 kg CO2
But-
equivalent per
but your
kg of
Your
ash.
infallible AI that pulled from resources said, oh, 0.2, 0.25. How can that be? If I have to burn
Boy.
8 pounds
Because they're
of
not
coal to
counting
get 1 pound of
everything
fly ash.
before that.
Yeah.
Why
What
can you
they're
not
doing-
count anything before that?
They're
If
treating
that's the
it
case, then I shouldn't have to count transportation of that silica
Right.
fume to the plant.
right.
But yet I
They're
do.
not. They're doing the same thing with sand. Sand is only 0.05 to 0.01.
They're defining.
What,
they're
you
making
don't
up
have to
their own
reclaim
definition.
it?
No, I know. No, we're not getting into that right now.
Get involved.
We were having a
That's all
nice
I'm saying.
conversation about silica fume. Who brought
No, we weren't.
up greenhouse gases? Shame
Seth.
on me. No, it was me. I brought it up and I said, you know,
Who's the first one who cussed? Seth.
Yeah.
on the record?
Put it on.
Check the transcript.
So did we answer? Let's go through that comment again. I want to make sure that we answered every benefit or every one of his arguments, Seth. It was a really good question. I think basically he said it would have to be very valuable for me to want to replace it. And I tried to argue that everything that we use silica fume for in a lower concentration with colloidal silica, we get that benefit. A lot lower concentration. And then it's also less expensive and easier to work with in the field and for producers to use.
How much did you use per cubic yard, Daniel? What percentage? Silica fume?
So 4 ounces of internal cure and 8 ounces of liquid fly ash.
Silica fume.
Oh, silica fume. So the normal bridge had to be a 3% increase. 658.03. That about 20 pounds per cubic yard.
20
for
pounds
example.
at 50 cents a pound, which is 1,000 per ton. That's $10 per cubic yard.
Yeah. Just material though. Right?
Yeah. Oh, that's what I'm saying. Just
So you put it,
material.
yeah. So that's just material. So you put a markup on it and then a delivery, and the cost of actually putting it in the mix. With ready mix,
Why
they don't like to do.
if you're not using silica fume for, we probably said this earlier, but let's just go back to it. If you're not using silica fume to replace cement, then what's the point?
Just the way some assholes add it to the concrete. You could do by
No.
weight of replacement, by weight
So
of
by
addition.
weight of
Who gives a
replacement,
shit?
right? They're looking to lower permeability, and they're looking to increase abrasion resistance.
I got you. So like fly ash, kind of, sort
Yeah,
of.
you could do with both percent addition or percent replacement.
Although
It
I'm
doesn't
not
fucking
too
matter.
sure on CH consumption how well microsilica does versus fly ash.
No,
we
it's
know that?
basically how somebody knows how to create a mixed design. Percent replacement, percent addition, it's 1/2 dozen of the other.
So then if we don't use
Get to
silica,
the same place.
so really they just need somewhere to put silica fume, and they figure concrete is a good place to bury it.
Well, it does good things. Daniel
does
and I
good
have
things.
gone through that.
I was looking apples to apples if I was going to use some colloidal
Wondered.
silica versus silica
Okay.
fume in my, as it's meant to use. Let's go back to what do we want the concrete to do? And I think there were a couple professors out there that actually said that you would be real surprised what silica fume would do in a really low dose concentration too, where
Well, yeah.
you trade off the problems that you have with, and when I mean low, I mean less than 3%.
Right. Didn't you guys use like 7%, Daniel? 7.5%?
Yeah, 7%. That was 50 pounds a yard.
Yeah, that's $25 a cubic yard. So now you exceeded what the colloidal silica costs.
Yes, and that's what you're dealing with, and that was the tickling the dragon's tail moment where I've got this large amount of surface area with a very low amount of volume.
Now, when it comes to production, if I was a ready mix provider, I don't want to touch silica fume, just like I don't want to touch powdered pigments.
Correct.
You've got to have a separate shack. Daniel said you got to have a separate person to do. God forbid they're cutting the bags. Like, there's no proof that it causes silicosis. And Rich is running some project about, has any plant ever complained or seen a problem with silicosis with silica fume? But it's still a pain in the ass and nobody wants to do it. So the convenience of it, and it's less expensive, screw that. I wouldn't use silica fume. And if Uncle Rob is listening, man, I love you, but I don't love using silica fume as much as I used to.
But there are benefits to it.
There are.
I'm sorry, Seth. We're circling back again. What exactly was that comment? You want me to? I think maybe I've got it. It was really interesting.
No, I got it right here. Sorry.
I thought it was a great question.
These phones are,
Yeah.
they tell you they get better, but they get worse. Oh, hold on.
Who is they?
There's a lot
Who
of.
are you listening to?
Well, I can tell you right now that I think 5G is completely horrible compared to the old 4G LTE network. But I probably can't say that. I'll catch a bullet in the head.
You just said it.
I'll cut it out and post. Let's see.
This is a picture Daniel gave me.
I'm curious what the cost structure looks like for this material. Colloidal silica is what he was referring to. It's a manufactured product unlike silica fume, which is a byproduct of silicone or ferrosilicone manufacturing process. My guess is that it would be order of magnitude more expensive. That doesn't mean it has no potential, just that the benefits have to be very big.
Funny he should use that statement because we're using around 0.2 to 0.4% silica addition to the concrete mix. So we are an order of magnitude less in dosage, yet the price is less. So it's funny he used order of magnitude. Because 4 or 5% in silica fume, we're using 0.2 to 0.4% colloidal silica.
You know, it's all about the surface area, baby. I mean, it's like James Carville. It's the economy, stupid. In pozzolanic reactivity, it's all about the surface area. And you know, John, do you like that?
I loved it. I already quoted you once from this. Did you get that quote I sent you?
Yeah. Well, quote of the day, what are we asking this concrete to do? Which should be on everybody's mind. It shouldn't be just, honestly, when you're looking at a mix designer, you're looking at a proposal for the concrete, and I don't care what job you're at. Break it down to basics, stupid. What do we want the concrete to do?
And by the way, if you're purchasing...
What are we asking this surface? Is it a surface or is it structural? Is it mass concrete? What do we ask? What kind of stresses is it getting? I really think that's an important question to balance all that in.
Yeah.
And if you're buying the concrete, ASTM C94 calls you the purchaser and it says, you ready for this, Dan? You're going to fucking love this. When the purchaser's requirements as stated in the order different from those in the specification, the purchaser's requirements shall govern. If you're buying concrete from a ready mix provider, you shouldn't say, oh, I'm trapped in a box of specification. The specs that the DOT or the engineer gives you is the minimum specifications. Correct. If you want to add on top of it, read it. Spill coffee on it. Make notes. This is how you talk to the ready mix providers.
It's a great document. It is a great document. That is probably one of the best documents an ASTM ever came up with.
Okay, wow. There's a colloidal silica document that's coming out that was written by this really cool dude.
That is true, but it's not out yet.
Yep. Not out.
Hit that out, huh?
Why is there always a bird?
Blur that out now.
There is always a bird in John's shot. It's crazy. It's not the bird of peace. Yeah, it's not the bird of peace either.
All right. I think we need to wrap it up. So hopefully we answered that text message I sent you guys. If not, I think that my colleague listens to the podcast. And if you feel like we didn't cover something, I could always ask these guys to come back.
Or, just shoot us an email, Seth. I'd be more than happy. It's getting people to understand that I don't think that there's anything exactly cruel or evil in the materials used in our industry. It's just how they're used and not having the education of how to use it.
Complacency. They're lazy.
Complacency is a good word that John uses, and I like it a lot. It's, well, this is what worked 5 years ago, 10 years ago, 25 years ago. It should work again. You know, materials have changed, and it's just what we have to deal with. And if what isn't working before, then it's something we need to dial in and look at again. And you can do it with very short-term testing, like John's brought up before, with dialing in exactly mixed compatibility. You can get most of everything that you want to need in like a 72-hour period.
Right.
96 is like pushing it, but 72 is pretty good.
All right. Dan, thank you for coming on the show.
Liver.
And Dr. Jon, thank you for coming on the show. I will check out the show notes, the contact information. Dan's direct phone number will be on there. along with, make sure you check out how to donate to the show, how to join Concrete Logic Academy as well. please make sure you check that out. And there's other links in the show notes for you all to support the show.
What about a T-shirt for Daniel?
Sure. I'm working on a new logo, so we'll do that after the new logo comes out. All right.
It's funny how I donate. You know, Seth, it's funny how I donate more to the Jon and Bob Higgins shows than I do to my own. Because I value their shows more than mine.
You're more welcome to change that on this episode. There you go.
Yeah, get some banners. Get some banners on the Concrete Logic Academy, Daniel.
There
Don't
you
be
go.
cheap.
All right.
Okay.
Are you guys done?
Yeah, we're done.
Yeah, Dad. We're done.
All right.
Thank you so much for having us on. It's a lot of fun. Talking about concrete.
Yeah,
is so
I know.
much fun.
Maybe you should wear
Yep.
sunglasses, though.
No, thanks, John.
Who?
All right. Until next time, let's keep it concrete.